In this lecture, I'm going to introduce the concept of chemical equilibrium. So, up until this point in general chemistry, we have really talked about chemical reactions as occurring from left to right, from reactants to products. We have thought about them as continuing until completion, that is to say, until the limiting reactant is used up. So, I want to kind of think about the way we've been thinking about reactions up to this point, and then challenge those thoughts a little bit. So as an example, I want to examine the decomposition of calcium carbonate to form calcium oxide and carbon dioxide. This is a really important reaction in industry. Calcium carbonate is a mineral, limestone, which you can mine. And when you heat it up, we're talking 500 to 600 degrees Celsius temperatures, it decomposes to make calcium oxide, which is lime, and carbon dioxide as a byproduct. So this decomposition reaction is hugely important because that's how you make lime for mortar. So industrially, lime is produced on a huge scale, more than 20 million metric tons in the United States alone every single year. And the point of this is to make the key ingredient for cement mortar, the stuff that cements bricks together and other construction materials. So this is a hugely important reaction. So we can think about this reaction as going to completion, but the reverse reaction also occurs where lime or calcium oxide can combine with carbon dioxide to make calcium carbonate. Okay, so the reverse of this reaction can occur too. Now, in principle, all reactions are reversible. And in principle, all reactions will eventually reach something called dynamic equilibrium. That's what we're going to define today, provided that all of the products remain available for the reverse reaction to happen. So, for example, if we are in industry and we're trying to make lime, we want to think about how we can prevent that reverse reaction from happening. We don't want calcium oxide to recombine with carbon dioxide because that would lower our yield of the desired product, which is the lime. So we can express equilibrium. We can express this idea of equilibrium using a double-headed arrow. So I'm going to write calcium carbonate and then a double-headed arrow going to calcium oxide and CO2. This double-headed arrow is how we express the idea that both the forward and reverse reactions are happening. So imagine you are an industrial chemist who wants to drive this reaction from left to right. You want to maximize your yield of the lime. How would you do it? Okay, well, let's draw a big industrial vat. Okay, so here's my big industrial vat. And we can imagine at the bottom of the vat, I have my calcium carbonate. Okay, so this is a solid mineral. Okay, so we have that kind of at the bottom of the vat. Now, how can I don't know why my machine is doing this, but there's my vat. All right, so how would you try to make sure that the reaction is driven in the forward direction, and how would you prevent the reverse reaction from happening? Well, the key here is to notice that the carbon dioxide is a gas, right? So as long as you do this in an open kind of vat, as the reaction takes place, you can be pretty sure that your oops, that your carbon dioxide as it's formed. Okay, so let's think about what's happening as the reaction takes place. Your calcium carbonate is transforming to form calcium oxide. They're both solids, so I'm just going to draw them at the bottom of the vat there. But the other product that you have, the waste product, is carbon dioxide, which is a gas. And provided I have an open vat, that carbon dioxide can escape from the container and kind of go into the atmosphere. So if the carbon dioxide escapes, it's no longer present to recombine with the calcium oxide. And that means that reverse reaction can no longer happen. So the carbon dioxide escapes, and this means that it's going to be not present anymore to recombine with the calcium oxide. So that effectively prevents the reverse reaction from happening. And this is what the industry's choice is, right? This is why the production of cement mortar is a major culprit in climate change, because you have a whole lot of carbon dioxide being driven out of smokestacks and into the atmosphere. And of course, carbon dioxide is a greenhouse gas that's associated with global warming. So the cement mortar industry is a major culprit. So would you call this an equilibrium system or a non-equilibrium system? Well, as long as we keep that vat open, the carbon dioxide is escaping and we don't have the possibility for the reverse reaction to occur. So this little kind of setup that I just drew would result in a non-equilibrium system. We would be driving the reaction forward with no possibility for the reverse reaction to happen. So how could we turn this into an equilibrium system? You could make it into an equilibrium system simply by sealing the vat, okay? If you sealed the vat, then your carbon dioxide would be trapped inside the container and it would be available for the reverse reaction to occur. So sealing the vat would give you an equilibrium system because you would have the carbon dioxide stuck inside your vessel and it would be available to react with the calcium oxide to push the reaction backwards and form the calcium carbonate. So I want us to think about what is happening in this reaction for a moment. Okay, let's imagine we have an equilibrium system. Okay, let's imagine we have an equilibrium system. Think about this reaction in a sealed container. As that container starts to be heated up, the decomposition of calcium carbonate begins. And at the beginning, there's only a teeny little bit of calcium oxide and carbon dioxide that have formed. So that's just not a lot of the products around to recombine with each other for the reverse reaction. But as the calcium carbonate continues to decompose, the amounts of calcium oxide and carbon dioxide become appreciable and they can start to encounter and react with each other more frequently. And eventually, if you're in an equilibrium system, you get to a point where the reverse reaction happens just as fast as the forward reaction. And when that happens, that means that the amounts of calcium carbonate, calcium oxide, and carbon dioxide are no longer changing. The system has reached dynamic equilibrium. Okay, of course, this only happens in an equilibrium system when you keep all of the substances involved in contact with each other. So we can graph what everything I just said looks like. All right, let's think about concentrations as a function of time. I want to think about concentrations of products and concentrations of reactants, both of them as a function of time. So at time zero, at the beginning, you have no products, but you start to slowly make products and eventually you kind of level out so that the concentration of the products is no longer changing. Sort of conversely, you start off with a lot of the reactants here. Wait, let me just make this a little shorter so that it actually fits on my axis. I'm gonna, same shape, but a little shorter. So you start out with no products and eventually the concentration of the products level out. Okay, so these are my products, the purple line. Now, I'm going to switch to a red line to draw the concentrations of the reactants. So at the beginning, you have a lot of reactants, but as they combine to form products, their concentration goes down. But eventually, as your products level out, so do the concentrations of the reactants. So that point at which the concentrations are no longer changing, so when both of these start to level out, that is the point at which equilibrium is reached, the point of equilibrium. So at equilibrium, the amounts of the reactants and products are no longer changing. Okay, that's very important. So the concentrations or the amounts of the reactants and the products are no longer changing. And that is because at the point of equilibrium, the other thing that's true is, so I'm going to write that down here, at equilibrium, the rate of the forward reaction, this is for any system, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. And that means that as a consequence, the concentrations of the reactants and products are no longer changing of the reverse reaction. So, like I said before, every reaction is reversible provided the substances are all kept in contact with each other. And this state of equilibrium is actually called dynamic equilibrium because both the forward and the reverse reactions are still occurring. It's just that the concentrations are no longer changing. So macroscopically, the equilibrium state is static. It looks like nothing's changing. But on the molecular scale, the reactions, both in the forward and reverse directions, are still occurring. So the system is quite dynamic. There's still quite a bit of molecular transformation going on. It's just that the rates of the forward and reverse reactions are equal at equilibrium.